Hello guys, my name is Arun and welcome to my channel. This series is a series of tutorials on Fortran programming. Now in this tutorial we will be looking at an example for the determinant of a matrix. Now in the last tutorial we saw how to find the determinant of a matrix using the slice operation and recursive operations and all. Okay, now in this tutorial we will be using the property of finding the determinant of a matrix, okay, to find the solution for a system of simultaneous equations. Now to explain you guys what's happening, suppose if you have a system of simultaneous equations that you can express like ax equals b, something of that sort. Okay, I'll just show you guys in Chrome. Solving a system of linear equations. Okay, instead it's a system of linear equations. Okay, I have a link in wiki. This will be really easy to follow. Okay, while this load I'll just show you guys. Suppose if you have a system of linear equations, okay, you can express that as a matrix X and as a vector matrix A, a square matrix A, and a vector X, and which will be equal to a right hand side matrix B. If you can express this, you can express a set of equations like this, then using if you know the determinant of A, okay, and if you are able to you plug in the values of B in different rows of A, in different columns of A, in a particular manner, and find the determinant by plugging these, okay, using those determinant values and the determinant value of A, it is possible to find the values of each and every variable easily. Now this is the system of linear equations. There will be for some now the equations are coming. It just took a little time, I suppose. Okay, suppose you have a system of equations like this one, like 3x plus 2y minus z equals 1, 2x minus 2y plus 4z equals minus 2, like that. What you can do is that you can represent this set of equations, okay, in the matrix form. What I'm doing is I'm representing this as this: 3 here, 2 here, minus 1, this coefficient here, 2 minus 2, 4 minus 1, 0.5, and minus 1. Okay, and on the right hand side I'm representing this 1 minus 2 0 as 1 minus 2 0 here. Now this way this becomes your A matrix, and your X matrix becomes your variables X, Y, and Z. Okay, and then your right hand side your B matrix is this 1 2 3. Now if you're now using this, Cramer's rule states that if you are able to replace the first column with B, okay, and then the second column with B, third column with B, like this. Suppose you have a matrix, you have the same matrix A, and then in the first column, instead of the actual values like 3 2 y minus 1, I just replace them with the matrix B, like this. I replace them with the matrix B values like this. Okay, I get a new matrix called as XA. Similarly, keeping that aside, if taking the same matrix A, in that instead of second column, replacing that with matrix B, I'll get a new matrix called as XB. I keep it aside. Similarly, in the matrix A, in this matrix, I keep the same taking the same A matrix, and in that I replace the third column with the matrix B. Okay, and let me name this XC. Now if you are able to do that, now what your variables X, Y, and Z are here: X1, Y1, Z, X1, X2, X3. Their values are nothing but the determinant of this matrix divided by A, like that. First will be the determinant of first variable's answer will be determinant of XA divided by determinant of A, and then it will be determinant of B divided by determinant of this matrix divided by determinant of B, A, and then we have determinant of xc divided by determinant of a. So this is how it will happen. Now this is what we are following here. Now this is the program. I'll just walk you guys through what happens here. This is the implicit none. This is where I set the order of the matrix. Just like in the previous example, I'm setting it for 3. I just introduce 2 iterating variables I, j for the loops. Okay. Now this is the matrix wherein I get all the where I store all the A matrix and stuff. If you guys notice, instead of 2-dimensional matrix, I'm taking a 3-dimensional matrix, because instead of defining separate matrices for, if you guys look at the explanation, instead of writing everything in separate matrices like XA, XB, XC and all, okay, what I do is that I just define that as a 3-dimensional matrix. Now this +1 stands for this +1 is for including the matrix A itself. Now if there are 3 variables, let's say, then and other than matrix A, I'll have 3 more matrices. So if you guys notice, if I were to club all this, I'll have 3 rows, 3 columns, and if 3 columns and 3 heights, kind of like that. Okay, your x-axis will be 3 units, your y-axis will be 3 units, and your z-axis will be 4 units, kind of. So if you guys notice, this matrix will become 3, and to include that kind of a feature, what I'm doing is I'm just putting a +1. This +1 is for putting A, whereas all the remaining n values is for storing all the matrices for x, y, and z, and so on. I hope you guys understood. Okay, and then I define 2 matrices with B and X. Okay, now just a little warning here, guys. Though B and X can be 1-dimensional, I am making them as a 2-dimensional array, and I'm using them as a matrix here by adding this 1 here. So I could have just defined like n, that will be sufficient, but I'm intentionally putting it as n, 1 to explain you guys that there is a small difference between a matrix and an array. Nothing much. Okay, now what I do is I just use this reshape command to set the values of A. Now I'm just taking this example over here in the Wikipedia to solve it. Okay, so I'm using that value here. I'm just rearranging it. Now if you n is 4 or 2, this kind of initialization won't work, but for running this program, setting like this, and then B, I'm setting the same B values over here. Simple enough. And then what I'm going to do, I'm just going to I'll come to this subroutine call little later. Here I'm printing all the matrix values value A comma B here, and then print the values of matrix XA, then XB, XC, and finally the solution. Now the major fun part comes in this call. I'm just calling a subroutine called as cram, and I'm passing 4 arguments into it, namely X, A, B, and N. Now if you guys notice, okay, where do I have this? I have this in this module. Now in this module, ignore these 2. I was experimenting with a certain stuff, but it didn't work out properly as I thought. I was getting some segmentation fault issues. Actually what I did, I thought instead of setting like this, I'll just, instead of assigning like this here, I thought, okay, I'll just set this equal to some function, and that function will automatically read the values from the user and set it here, so that this kind of stuff might be easy if you have multiple simultaneous equations and all. For now, if I just showing some segmentation fault errors, I am pretty sure, I'm not pretty sure as to what exactly is going on, but anyway, as of now, ignore these. Now this is the same recursive function we used to calculate the determinant in the previous part, and this is the slice subroutine, the same slice subroutine which we used in the previous example to find to slice the matrices, and this is the new subroutine we put. This subroutine calculates the solution by continuously calling this determinant function, and by impliedly calling slice this slice of subroutine through this function. Okay, now I'll explain what's in this. I'm just putting an implicit none. I'm just getting this value as an integer with the intent end condition, and this is the important part. I'm getting this matrix A as a dimension of the same order, same size as mentioned here, but I'm giving an argument called as intent in out, meaning this value of A will come in with this matrix A, or this variable A will come in with with certain values, and when it exits out this subroutine, it'll go away with a new entirely different set of values. Okay, and this how the values will change depends on what kind of an alteration has been made to it by the series of commands that allow it. And then I define B, and this time I'm defining B as an array, a one-dimensional array alone. Okay, this is just a small change, but nothing to be surprised about. And then I'm defining the external function det_f for which is nothing but the determinant function. This function is external to this subroutine, so I'm defining it here. And then I'm defining this integer variable for an iteration process, and then I'm defining x which has a dimension n, 1. Okay, this as a matrix, two-dimensional matrix, and I'm setting it as intent out, meaning it comes in without any value, and it goes out with a value. Simple as that. Now this is the part. What I do is that firstly, in this operation, what I'm actually saying is that see, if you guys notice, only the first row, column, height, whichever. Okay, I call it height. You can call it anything you want, but okay, the height one alone is actually initialized here, whereas the height 2, height 3, height 4, they are not initialized. Okay, now but if you want to find xa, xb, xe like that, if you guys notice, what you have to do is that copy this value everywhere, copy this value to all the heights, and then change only one set of columns. Simple enough. So I am doing the same here. What I'm doing is that in this do loop, the first step, I'm copying the first heights value to all the heights. So it will copy to the height 2, then height 3, and then height 4, like that and all. Okay, like that and all. I'm using the term height to express the third axis, but you can use something like page or book or shelf or paper, whatever. Different programming languages have a different convention to name the third axis. So you guys call it whatever you want, as long as it makes sense. Okay, then what I do is that I change the ith column of every page with the matrix B. Now what this will do is that, okay, in this step what it will do is that it will just copy the matrix A to all the heights. In this step it will just copy the value of B, and it will replace the ith column everywhere. For instance, B will be copied to the first column in the second height, and then the second column of the third height, and the third column of the fourth height, and so on. So this is exactly what we want. We just want the first column of the second height to be filled with B, and the second column of the third height to be filled with B, and the third column of the fourth height to be filled with B. Now I'm to explain the same, that's why I wrote this statement here. A colon comma 1 is the first height, wherein it's a two-dimensional matrix, that is the value of A. And then for XA, what you have to do is that replace this column with B. So in second height, since all of them are initially made equal to this, in the second height I just remove the first column values and replace them with B. Now with the third height, what I have to do is that if I want to get this, the third height, what if I want to do, I get this, I just have to copy all this to third height, this entire thing to third height, and then instead of second column this value, I have to replace this with B, and that's why I have it. So that's why it's second column. Like that, I have to copy everything to this value, copy everything to the fourth height, and replace the third column with B. Simple as that. Similarly, suppose if there are like 15 rows or 15 columns like that, this do loop algorithm, this do loop will take care of it. And then finally, this is where the value of x, y, and z, the values of the solutions are calculated. What it simply does is that it just calculates the determinant of that particular height under consideration, okay, and it returns the value here, and that value is divided by the determinant of A. Simple enough. Fine. Or else what we can do is that to make this job a little simple, okay, all I can do is that I can just type real 8 det underscore A, and I can set this as det underscore A equals this, and then I type det underscore A. Simple enough. So that I'm not running this again and again. Okay, once I calculate this, and I'll be using this here, so that this slow doesn't put too much overhead during the recursion process. Okay, and that's it. Now it will calculate, by Cramer's rule, it will calculate the this is exactly what will be followed here. It will just calculate the determinant of the second page divided by the determinant of the first page, and then determinant of third page divided by determinant of first page, like that. When essentially the determinant of XA by A, determinant of XA by divided by determinant of A, determinant of XB by determinant of A, determinant of XC divided by determinant of A, so on and so forth. Okay, now this value in this subroutine, well, by doing all these operations, your A is changed, B remains unchanged, N remains unchanged, and your X remains changed. So that way, when you call this subroutine cram in this function, your X gets changed, A gets changed, not the first page, but not the first height, but all the remaining heights gets changed, B remains unchanged, and N remains unchanged. And then I'm just printing up all these values. Alright, now, and to run all this simple manner, what I do, I have written a simple shell function, shell script, just like in the previous tutorial, and I made it okay, and I kind of made it executable. If you guys notice, I made it as an executable here. So all I have to do is that bash, okay, Cramer sh, okay. If I run this, click enter, and it will work fine. Okay, it just lists out all the files that are available, removes mod function, any mod files or .o files or .exe files if there are any, and then it will just list all the files, then compiles these two files and builds it to produce an executable called as Cramer.exe, and then runs the executable, and because of the formatting features available here, because of the formatting features I kind of introduced here, okay, it becomes a little fancy. The output becomes a little fancy. Okay, now the matrix A and this pipe symbol, I'm using it to represent, separate that from B. Okay, now this is this part is matrix A, and this is actually matrix B. Now this is matrix XA, this is matrix XC and XB and matrix XC, and the solution is actually at the bottom. Now if you guys look at, this is where matrix A gets printed, matrix B gets printed here using this code. Similarly for matrix B, so this is matrix A, sorry, this is matrix XA, this is matrix XB, this is matrix XC, and then the solution gets printed here. Simple enough. Alright. As usual, I actually try to explain, run this by explaining, by typing all this and explaining you guys, and you know, these are getting pretty much messy and complicated. So by the time I finished, it took me so much time. So that's why I'm explaining guys like this. Hope you guys understand. Okay. If you guys have any questions or doubts, you can just ask me in the comment section. I'll do my best to answer all the questions possible. Okay. That's all I have for you guys in this tutorial. Thank you guys for watching, and I'll see you guys in the next tutorial. Bye. And one more thing, do subscribe, please do subscribe. Thank you.